2004 exam, 2004 exam. Let's go. So we want to get this rope L. The person's going to swing down or grab a stone and then land in the lake. I have no idea why a person would do this, but we're going to ignore that fact. So this person's an idiot. So a rope of length L is attached to the support cord, blah, blah, blah. So let's get the speed of the person right before they hit the object. And to do that, we're going to actually use conservation of energy. So m1gl equals 1/2 m1v squared. The m1's actually cancel, and we're going to get that v equals the square root of 2gl. So that's good. So let's get the tension in the rope right before the collision with the object. So this thing's moving in a circle. And so what that means is, if we were to draw a free body diagram of the object, we would have the tension going up, and we would have the weight of the person going down. And so we'd have T minus M1G equals MV squared over R. Now for R, we put in L, and for V squared, we put in 2GL. When we simplify that out, that means that our tension is going to be 3 m1g. Now let's get the speed of the person and object just after collision. To do that, for part C, we use conservation of momentum. So m1v1 equals m1 plus m2 times that final v together. Well, we know that v1 is this square root of 2gl, so the final speed after they hit and stick is going to be m1 over m1 plus m2 times the square root of 2gl. That's nice and messy. That's just great. Now, for D and E, we want the total horizontal displacement of the person when they land in the water. So I'm actually going to get that last, and I'll do first, and then I'll do D last. So what I want to say is we fall through a distance L. So L is going to be 1/2 gt squared because we're falling. So what I'm getting is that 2L over g under a square root is the time. So that's the time it takes to fall. So what we're going to say is x is going to be L going from here to here plus whatever I get. So that's going to be actually v after the collision times t. So it's L plus vf times t. So the total x displacement is going to be L plus m1 over m2 plus m1 times square root of 2L over g for the time, times square root of 2GL for the speed here that I'm putting in, times the square root of 2L over g. So the square root of g cancels, and I'm actually going to end up getting, when I simplify this, x is going to be L plus m1 over m2 plus m1 times 2L right here. I could put this over a common denominator if I wanted of m2 over m1, but I'm actually happy if you leave it like this. I guess for the sake of aesthetics, the way I'd want to see the answer to part D is I'd want to see the answer to part D as C, 3 m1 plus m2 over m1 plus m2 times L. That's how I'd want to see the answer to part D. I believe I simplified that fraction right, so that's 2m1L plus. Yeah, I think I did that right. So that's kind of how I'd want to see the answer to D, and I think that's how the AP people would want to see it too. Now, this is for part E. For part D, I'm actually going to go ahead and do that on the next page. So the way part D works, I know that V1 before the collision is square root of 2GL, and I know that the V final after the collision is, if I simplify this right, m1 over m1 plus m2 times the square root of 2GL. So if I want to compare the kinetic energies, so KE before is going to be 1/2 times m1 times the square root of 2GL squared, which is that. And KE after is going to be 1/2 times M1 plus M2 times, I got a lot to square here, this is going to be M1 over M1 plus M2. I got to square all of that, and I got to square 2GL here, and so I need to get this ratio, which actually ends up being pretty obnoxious. So I'm actually going to leave it to you to simplify that, and I'll post the solution online in this PDF file that I'll actually upload. So we want the before versus after energy. So we want this fraction, KE before over KE after. And I'll actually let you know what that is on the PDF file, but I want you to actually try to check it and get it for yourself.